Take a look at example 4. Here we're given a vector 2, negative 6, 3, and we want the unit vector parallel to 2, negative 6, 3. This is good practice for figuring out how to find the unit vector in a given direction. The unit vector will be the vector itself divided by its magnitude. So we're going to divide the vector by its magnitude. Using the formula for magnitude, we're going to just write down the original vector again, and then the magnitude is the square root of 2 squared, which is 4, plus negative 6 squared, which is 36, plus 3 squared, which is 9. So 2 squared, 4, negative 6 squared, positive 36, 3 squared is 9. If we add these numbers under the square root, we have 36 plus 4 is 40, plus 9, 49, and we're taking the square root, so we have a 7 in the denominator here. After simplifying, we have 2, negative 6, 3, divided by 7, and we can write this all out if we think of distributing a 1/7 to all the components. So we'd have 2 over 7, negative 6 over 7, and 3 over 7. That is a unit vector. The length of that vector is 1, and it's parallel. It's in the same direction as the given vector. We know that it's parallel because it's just a constant multiple of the given vector. And if you check by taking the magnitude here, you'll find that the magnitude of this vector is indeed 1. It is a unit vector. Let's check this out in GeoGebra. So here in GeoGebra is our original vector 2, negative 6, 3. Notice that GeoGebra gives us a name. It calls this the vector u. We can actually use that to graph the unit vector. The unit vector is 1/7 times this original vector because this vector has a magnitude of 7. So we could simply type in 1/7 times u, or even just u divided by 7, and GeoGebra will graph in the unit vector for us. So there's the vector of length 1 that's parallel to the original given vector. Let's solve example 5. We want to find a length 7 vector u in the first octant. So first octant just means that x, y, and z are all positive. And we want this vector such that it makes a 45-degree angle with all 3 of the x, y, and z axes. And we want to figure out what is the component form for such a vector. Let's try to graph this out and see if we can visualize what's going on here. So we'll graph the x, y, z coordinate axes. And we want the vector in the first quadrant, which has a 45-degree angle with all of these. It's kind of tricky to visualize again on a two-dimensional surface like this, but just imagine a vector coming out here where we've got a 45-degree angle with the x-axis, there's a 45-degree angle with the y-axis, and a 45-degree angle with the z-axis. How do we get such a vector? We want one of length 7, but how do we get any kind of vector like that? Let's drop it down a dimension. Let's think of just 2 dimensions. How would we get a 2-dimensional vector that makes a 45-degree axis, 45-degree angle with both the x and the y axes? Well, that would look something like this. What sort of a vector could that be? It would be a vector where the x and y components would have to be the same. We could have a vector such as, say, 1, 1. It might not be length 7, but at least it makes a 45-degree angle with both the axes. And then we could scale this by an appropriate number to get it to be length 7. That's what we're going to do in 3 dimensions. First, we're going to find a vector that does make a 45-degree angle with all the axes, and then we're going to figure out what do we scale it by so that it's length 7. So can you think through what would be a vector here that would make a 45-degree angle with all the axes? If we're not worried about length, we just want some vector that makes 45 degrees. Well, the vector would be 1, 1, 1. If we take the vector 1, 1, 1, this makes a 45-degree angle with all of the different axes. Again, it's tricky to visualize in 3 dimensions, but imagine going 1 in the x direction, 1 in the y direction, and 1 in the z direction, and we'd have a 45-degree angle with all of the axes. Now we want to know, what do we scale this vector by so that it has length 7? Here's what we'll do. First, we'll find a unit vector parallel to this, and then we'll multiply the unit vector by 7. Multiplying a unit vector by 7 gives us a length 7 vector. So this vector is in the right direction, it's just not the right length. Let's first make it a unit vector by dividing by the magnitude. So now we have a unit vector if we divide by the magnitude. Multiplying a unit vector by some number scales it by that number. So if I multiply a unit vector by 5, it'll get me a length 5 vector. Multiply it by negative 2 gives me a length 2 vector in the opposite direction. So we want a length 7 vector. We're just going to scale this entire thing by 7. This looks kind of complicated here, but all we need to do is find the magnitude of the vector and then divide by the magnitude and multiply by 7. We'll have a length 7 vector. Let's work through those steps. First, we want the magnitude of the vector. To find the magnitude, we take the square root of 1 squared plus 1 squared plus 1 squared. That is the square root of 1 plus 1 plus 1, which is 3. So we have square root of 3 in the denominator. So 7, I'll take the square root of 3 out under the 7. We have 7 over the square root of 3 times 1, 1, 1. And now I just do scalar multiplication, distribute this, if you will, to all three components. And we get the vector 7 over square root of 3, comma, 7 over square root of 3, 7 over square root of 3. Since the x, y, and z components are all the same, since they're all equal, we will have a 45-degree angle with all three of the x, y, and z axes. And let's just double check to make sure that we got a length 7 vector. Let's check the magnitude here. We want to find the magnitude of the vector 7 over square root of 3, 7 over square root of 3, 7 over square root of 3. So we'll square all of these components and take the square root of the result. So if we square 7 over square root of 3, that's 49 over 3. And then add that to 49 over 3 plus 49 over 3. This looks like we might be getting into some tricky algebra here, but I really just have three fractions, which are all the same. So it's 3 times the fraction 49 over 3. So we have the square root of 3 times 49 over 3. The 3's cancel. We have the square root of 49, which is 7, exactly the magnitude that we wanted. So the vector that makes a 45-degree angle with the x, y, and z axes in the first quadrant that has a length 7 is this vector right here. Once again, we found this by first dividing the vector by its magnitude to get a unit vector, and then we scaled the unit vector up by 7 to get a length 7 vector. Let's solve question 6. What angle does this vector make with the x-axis? We can just assume, since there's no k component here, that this is a two-dimensional vector. So let's think of drawing this out in 2 dimensions and try to find out what angle does this make with the x-axis. We'll first draw the x and y axes. And the vector 3i plus 4j, I'm going to just convert that to component form. 3i, the I tells us the x component. So we have 3 for the x component. The j tells us the y component. So we're dealing with the vector 3, 4, which is something like right about here. What angle, theta, does this vector make with the x-axis? How do we figure this out? The way to do this is to think of this as a triangle. We have a hypotenuse and we have a right triangle here, and the x distance, that's 3, and the y vertical distance is 4. So I could find, for instance, the hypotenuse. We have a 3, 4, 5 triangle. The magnitude of this vector would be 5. But I'm not interested in the magnitude. I want the angle. What's a trigonometric relationship between the angle theta and these lengths of 3 and 4? What relates opposite and adjacent to an angle? That would be tangent. So we can say tangent of theta equals the opposite 4 divided by the adjacent 3. So theta is simply the arctangent of 4/3. That's the answer for the angle that this vector makes with the x-axis, arctangent of 4/3. Let's think of a slightly more applied problem with question 7. A shopper pushes a cart with a force of 25 newtons at an angle of -30 degrees to the horizontal. We want to find the vertical and horizontal components of the resulting force. For example 7, let's start by drawing a picture. We're going to think of the cart being moved along the x-axis. So we'll draw on the x-axis here. We're told that the force is -30 degrees to the horizontal. And we can represent this force using a vector. So here's a vector. This is -30 degrees. The magnitude of this vector is 25 newtons. That's the length. We're representing this force with a vector. So let's add the y-axis in here. We want to find the horizontal and vertical components of the vector. Let's draw those in. The horizontal component is just the x component here. Let's call this x component A, and the vertical component, that's the y component here, we'll call that B. If we want to represent this vector that we've been describing with an angle and a magnitude, if we want to describe that in component form, that would literally be the vector AB. So we're trying to translate from direction and magnitude to the component form. The key is to think of this as a right triangle. We have an angle here of -30 degrees. 25 newtons is the hypotenuse. we have an adjacent leg of A and an opposite leg of B. So for example, A, how can we find this? What's a trigonometric relationship that relates the angle with A and the hypotenuse? How about cosine? Cosine of negative 30 degrees equals adjacent A over hypotenuse. So we can say cosine of negative 30 equals adjacent over hypotenuse. I can solve for A by just multiplying the hypotenuse length on both sides. 25 times the cosine of negative 30. Cosine of negative 30 is square root of 3 over 2, so I have 25 times the square root of 3 divided by 2. That is the horizontal component of the force. And this is the amount of force that actually is moving the shopping cart. The B, the vertical component, is just going downwards into the floor, being dissipated as heat. If we think of this force acting on a shopping cart, then the only thing that's really moving the shopping cart in the horizontal direction is the horizontal component of the force. So we're figuring out how much of the force is actually acting on the cart. That's the horizontal component. Let's solve the vertical component of the force, B. The relationship between the angle and the hypotenuse and B is sine. We can say sine of negative 30 equals the opposite, B, divided by the hypotenuse, 25. Once again, solve for B by multiplying both sides by the hypotenuse. 25 times sine of negative 30. Sine of negative 30 is negative 1/2. So we have negative 25 divided by 2. Here are the vertical and horizontal components of the force. We can write this same vector, which we described with a direction and a magnitude. We can write that vector now in component form. The vector AB is, well, the x component is 25 times square root of 3 over 2. And the y component, negative 25 over 2. There are the horizontal and vertical components of the force. And it'd be a good idea to write newtons here afterward to remind ourselves that this is describing a physical quantity, a force vector.